A few words. So yeah, Christos is involved in a project called Beehive, which I believe is based on the old Maxine. So they have been working in Manchester on Java virtual machines. And we have had the talk by Juan a while ago. So there's also a little bit the whole cross computing devices from GPU to FPGAs going on. So, and I think, if my understanding is correctly, the project Beehive brings that all together. So yeah, Christos.
Yeah, please go ahead.
I'm happy to hear more.
Thank you very much, Stefan, and thank you very much for inviting me. Stefan placed it very well. So Beehive is, I would say, is an umbrella project. It's a collection of different projects that we run from different academics within our group, that they actually fall into the unified vision we have regarding how to do research. So I can start if I may.
Yeah.
So maximize. So my name is Christos, and I normally have two hats. One is from the University of Manchester, where I'm a senior lecturer, and the other one, I work as an architect at KTM Innovation, where we actually build systems for motorbikes. So if you're into motorsports and motorbikes. In this talk, of course, I will talk about our work that we do at the University of Manchester. And I will start giving a little bit of history of myself. So what I have been doing the last decade, and how this work led to the motivation that later became the project Beehive. Then I will talk a little bit about the challenges, at least from our perspective, and how we see computing in general. So which are the challenges in designing systems, and deriving from those challenges, how we actually came up with a vision of Beehive, and which components we actually develop to assemble all the pieces of the puzzle. Then I will talk about two use cases, like two works that we have done out of many to showcase how we use Beehive actually to do our research. And the last bit, which I think I will need a bit of your help as experts in building systems, it's a bit of reflection, which is something that we have been doing a lot within our group, and to try to actually answer the question whether all this effort, energy, and investment that we put into our open source infrastructure is actually worth it. So a little bit of history. I started my PhD, so I finished my first degree in Greece, which wasn't computer science. It was like a mixture of economics and informatics. So I didn't have a lot of like a good background regarding the core fundamental computer science courses, let's say. So then I went to Manchester for a master course, and I was really fascinated by virtual machines. So I started doing my PhD after I finished my master course. And that was back in 2006, where let's say the first, doomsday predictions about the silicon started coming into, let's say, it was more prevalent in scientific papers. So everybody was talking about the ends of Moore's law and the dark silicon, and how we cannot scale our chip manufacturing process anymore. And therefore, they were trying to, let's say, come up with new solutions how to solve this problem, because the performance we're getting from each generation of processors is becoming smaller and smaller. So that time, I was thrown into the whole, let's say, frenzy of transactional memory. There was like a lot of papers, like thousands of papers regarding software, transactional memory, and hardware transactional memory. And the whole research on parallel programming models, although it wasn't something new, but they were trying to try new things, how to speed up execution with a new Pegas programming languages. So I was thinking back then, oh, okay, that sounds interesting, and yeah, it looks like a serious problem. So I also jumped into this train and trying to do research specifically on distributed software transactional memory. And by looking at these papers, all those years and everything, then there were like hundreds of papers regarding how to do support in hardware, to do, let's say, transfer memory and speculative execution. And later, after 5-6 years, the first, let's say, products with Intel and IBM, they started coming out regarding how to implement some very basic form of the papers that were being written in the past in terms of hardware. And then I realized, okay, that's good, but I really lack background on chip design. So I need to learn more about how to design chips and to learn serious microarchitecture. So I decided to try to join Intel, and I was lucky enough to jump to Intel Labs in order to learn more about architecture. So when I went there, they asked me, do you know about hardware? I said, no, nothing. I said, what do you know? I said, I know how to write programs. So I said, okay, no problem. We're gonna teach you here. So the best way to teach you, if you are clueless about architecture, is to drop you into a team that does simulation. So you have to write a software simulation of a new chip that we're designing. And that was a really good exercise for me, because I had the opportunity to learn very fast and very complex topics. And back then at Intel, we were designing a new chip that it was, let's say, the style of transmet architectures, which, in case you don't remember, there were some, let's say, novel architectures back in 2000, where essentially you would have a dynamic binary translator and an optimizer inside the chip. So you could take, for example, x86, translate them to VLIW, so a very long instruction word, and then you would optimize the assembly on the fly at the instruction level, and then run them on the hardware. And when I finished the work on the simulators, then I joined the compiler team, the dynamic binary optimization team, and then I realized that the code that was coming from the compiler, which was assembly at that point, then we were running an interpreter to dynamically translate them into VLIW. And then after we had the interpreted sequence of instructions, then we were doing again another set of optimizations in the process, which some of them were standard, like a loop unrolling and all this kind of stuff. But some of them, they were very, I would say, very smart, because you had the opportunity, because you were very close to the hardware, to actually piggyback the hardware and then try to detect phases of your application and optimize the code on the fly and replace the previous code that you're running with a new code. So then something clicked in me, say, okay, so the Moore's law is dead and the performance deltas are not enough. Although it's true, like partially, in reality, there is a lot of performance still to be gained. So if you design your chip smarter, you can actually get significant performance improvements, even with the same process, node process on your chip. If you apply some, let's say, smarter, or at least you are closer to the hardware, you can do more aggressive optimizations. And then I said, okay, now I am, that's nice. That's a very good information. Now I have to learn about compilers. So I have to jump to another team now to learn about compilers and how to actually learn about aggressive optimization and speculations. So I joined the Oracle Labs, and I joined the team, the Graal truffle team, at the early stages. And the Graal compiler, it is a very aggressive compiler. It does a lot of speculative optimizations. So I worked there, and I could learn about those optimizations and how to apply them. And I started assembling the whole picture in my mind, like, okay, we have the hardware, the capabilities. Now we have the compilers, the programming languages. So now the missing part that I could see by working in these two different teams was that there were no synergy. So the hardware guys, they had the blind spot of the code that was coming. So they didn't have any semantics. And the software guys, they were not very familiar or expert of how the hardware expects things in order to optimize better and get the maximum performance that you can out of your hardware. And then, okay, let's go back to the drawing board and start thinking of what kind of tools we need in order to co-design the stack, in order for a researcher like us, for example, to run something and then get a report that how performance and other, let's say, characteristics of the execution, they were translated from the high-level programming language to the actual hardware. So then we went to Manchester, and then with other colleagues, we started thinking about this vision and what we want to build in terms of a stack that would help us answer these questions. So before we design, we try to put down in a piece of paper the kind of challenges that we believe we have when we design systems in general. And the first challenge was the obvious one, is that the horizontal performance deltas from hardware or software nowadays, they are much smaller than it used to be 20 years ago. So let's say a new generation of processor, it is maximum 10-15% faster than the previous one, the same with compilers. So we don't see anymore these 2x and 3x we were seeing back in the day. And nowadays, we don't design only for performance. So now we have to design for many other factors at the same time, for performance, energy efficiency, security, reliability. And when you take a step back and you think about all those factors, you realize that any solution I put affects each other. So then it becomes like a balancing act, and we have to be able to have some tools and methodologies to get this balancing act faster. At the same time, GPUs and nowadays FPGAs, they are coming into mainstream. Like they are, at least for the GPUs, they are everywhere. Even a commodity laptop can have 2 GPUs. FPGAs are more on the cloud, but they are coming slowly into, let's say, commodity hardware. The workloads have become much more complex. Nowadays, we don't talk about, let's say, spec benchmarks. I mean, we talk a little bit, but there are much more complex applications to evaluate, like AI, big data, computer vision. The software stacks are becoming more and more complex. So now you run something, you write an API that is being transformed 500 times because it actually becomes Java bytecode to run on the hardware. And if we take all of those and we try to do it vertically, so if we say, okay, don't worry, we're gonna build teams of experts from software, from compilers, from VMs, from hardware, optimizations, everything to build the most efficient chip or stack possible, that's not feasible, at least from my experience from an academic perspective, because it's very difficult to gather in a group, at least in a small group like ours, such a vertical expertise. Even in companies, only few companies have this ability to do it. And the recent examples of Apple's M1 chip and the near coming collaboration between Samsung and AMD to put the AMD GPUs into the Exynos chip, they are, in my opinion, proof that if you have this kind of teams and expertise and you put them together, you can actually, within the same power budget, you can get, let's say, much more performance that you would get if you didn't have this kind of integration, especially when it comes to heterogeneous acceleration and be able to partition your code into the different accelerators. So essentially, the isolated teams of hardware designers and software designers and compilers, nowadays it's a bit hard to at least make a case of how to get the performance out. And again, the problem, the challenge is not only performance. You have to design in this space between performance, energy efficiency, reliability, security, and everything. And every time you try to push, let's say, performance higher, how would you do it in hardware? You would make everything bigger, more cores, more cache, more memory, bigger buffers, bigger pass predictors. But at the same time, you sacrifice power. So you have more dynamic linkage, more static linkage, energy, and then the same for security. If you want to buy an automotive processor that has to be ASIL-D graded, then you have to have redundant execution, lockstep execution. You have to have 2 times the cores in the same die in order to guarantee that your autonomous driving pilot, it will not crash you on a tree because the hardware had a failure. So you have to design everything into this space, and therefore we need tools for that. So we need tools in order to help us, the researchers, to propose solutions of how to reach this co-design solution. And through this need, we came up with a Beehive vision. So if I try to squeeze the whole vision in one sentence, I would say that the Beehive, the aim of Beehive, it is to provide an extensible state-of-the-art infrastructure for hardware software co-design research. So we try to build a collection of tools that they fall into the same platform that can help us, the researchers, to propose solutions that span across the whole stack of programming languages to hardware in order to propose more efficient and more high performance solutions. So the objectives, so the design points around which the Beehive stack evolves, it is to, of course, support traditional and emerging application workloads. So try to be as, let's say, inclusive of programming languages and runtime environments and different stacked architectures that run on top of, let's say, fundamental runtimes we can support. It has to be multi-ISA, so we have to be able to support at least the largest number of the most modern ISAs like ARM, different versions of ARM like 32-bit, 64-bit, RISC-V, x86, and also multi-device like GPUs, FPGAs, and everything that comes as the years pass. And we have to put modeling and models in the system to co-design for power performance, security, and reliability. It means that we have to have tools that they can provide with a very high degree of certainty and accuracy also the performance. So it doesn't matter if you have a stack that you can, let's say, produce a number, if this number, it is 2x or 3x from the reality. So from the current modern tool. So at the same time, you have to be experimental, but on the other hand, you have to be able to be close in performance, at least with the current state of the art, in order to be able to convince people that your proposal is sound. And for most of the cases where if you have, let's say, to do architectural research, you need some infrastructure for simulation to be able to prototype solutions fast in hardware, in simulators, in order to propose features in the hardware or new hardware units or whatever you need in order to propose your solution. So this is an overview of the Beehive stack. I'm not leading all the components, of course. I'm leading some of them. So if you have questions for some that I don't know, I can redirect you to the people responsible. But essentially, there are 3 layers. I would say 3.5 layers. So the first one, it is the applications, what we support, or at least what we want to support, including different programming languages, different kind of domain of applications, different kind of frameworks for analytics and big data. The second layer, it is the runtime layer. So there we took some decisions of where to, let's say, place our bets in order to have an infrastructure that it can help us do research fast, but also be as close to the state of the art as possible. So in that case, we work with Maxim VM OpenJDK through Truffle and Graal to get the Java ecosystem and other programming languages running on top of the JVM. We try to integrate different memory managers into the whole infrastructure. Of course, we have Tornado VM that Juan talked a month ago for acceleration on GPUs, on FPGAs, and this acceleration is for Java and any guest language that can run on top of a Graal VM. We also have frameworks that we integrate underneath our runtimes for acceleration and then simulation. And at the lower level, We have the compute platform where we have real architecture, like real hardware we run, and also simulated architectures. And in this simulated environment, we have a combination of tools because simulators, they are a bit tricky. You have to trade between accuracy and speed. So the more accurate, the slower it is. So you have to have both worlds, both, let's say, fast and less accurate versus slow and very accurate in order to do your pathfinding, and then after the pathfinding to implement it properly to see what are your realistic numbers. And of course, you can also emulate architectures like features by having binary translators or optimizers that you can experiment with new cache hierarchies and new path predictors and this kind of stuff. And all of that, this whole stack is actually enclosed in the big circle of trading, power performance, security, and reliability. So any feature that you want to test, about any idea you want to test, you can actually implement bits of it, of the solution in every layer of the stack, or fully at one layer of the stack, run it, then have the result, and then you know exactly what you got and what you traded for that. So I got X performance, but I traded 20% more energy power consumption. So, and this is the actual target. So as I said before, in the application layer, we support, let's say, the majority of the benchmarks. You will see my slides are more Java oriented because I work more in the Java domain, but anything that can run out of the box, mostly we can run it. There are some cases or some benchmarks that they require a bit of extra support at the simulator level, especially if they are very multi-threaded and they do a lot of atomics, but yeah, this is implementation. We support multiple guest languages. Unfortunately, we cannot support, or at least we don't claim support for every possible runtime that Ruby or R or JavaScript have. So I assume if we run V8 in our infrastructure, probably we will not have the same coverage as if we run JavaScript through GraalVM, for sure. But in order to be able to consolidate the infrastructure and be able to provide more for less, when I say less, I mean less effort, we normally run through GraalVM. And of course, we have a lot of backends for acceleration like OpenCL, PTX for CUDA, and SPRV. We have implemented from scratch benchmarks suite for specific kind of domains, most notably for computer vision with SlamBedge and the Viola Jones. And of course, we do a lot of work with for Java-based frameworks for analytics and databases like Apache Flink, Spark, and Neo4j. So for the runtime layer, we use the Maxine VM. So when Oracle stopped officially supporting it, then we took it under our umbrella, and then we started building on top of Maxine VM by adding more backends like ARM and RISC-V, improving its performance, the compiler, backporting Graal compiler into Maxine VM, and all MMTK, which is from JAIX, the memory manager from JAIX RVM to Maxine VM. And in parallel, we started developing again from scratch Tornado VM. So Tornado VM, as Juan said, accelerates JVM-based applications. I will not say Java because technically we can accelerate through the GraalVM any guest programming language. So the idea is to have the common denominator, which is called Graal compiler, and use it both for acceleration and for, let's say, I will call it vanilla compiler research on normal CPUs. We have also implemented 2 dynamic binary translators and optimizers, especially for ARM, because for Intel x86, there were a lot of tools, like good tools like Pin, but for ARM, there were not many. So we implemented Mambo and Mambo 64. Actually, Mambo 64 is not open source because it has been commercialized. And we have developed tools in the simulators for system level profiling and DVFS management, and the memory profilers, and the models that can help us to increase the accuracy and the confidence and cross-validate the core models we simulate with real hardware. Talking about hardware, of course, we have the real hardware for the, let's say, the normal experiments, and we have the simulators. For simulators, we have integrated two, Gem 5, which is very, let's say, very famous. It's a full system simulator with OS and everything. And also we did integration of Maxine and ZSim, which is another simulator, trace-based, to make Maxine. So this is much faster than running Gen 5, and also ZSim it has been validated against real hardware, and it's in the ballpark of 3% performance difference. So we trust the numbers. And on top of those two simulators, we have a third one, which is, let's say, more advanced in a sense that you run the application on your on the hardware. Underneath we have Mambo, which is a dynamic binary instrumentator, and then we take the instructions that we run real time, and then we send them into FPGA. And in this FPGA, we actually model different hardware characteristics, like a new cache hierarchy or a branch predictor. So that means that at real time, when we run the application, we can actually at real time run simulation models at the same time. So that was a little bit about the general infrastructure. I have put references at the end of the presentation where you can read some of the tools and papers that link to those tools and how we use them in order to do research. So now I will talk a little bit about two use cases that we have, let's say, two research outcomes that are based on the Beehive stack. The first one, which I wasn't planning to include in the presentation when I started doing the presentation, but I was motivated because 4 days ago, Red Hat sent an email to OpenJDK because they wanted to initiate a new project called Lilliput in order to remove the memory footprint of Java objects by compressing the object header of the object, which it was perfect because that was exactly the paper that we have done like 3 years ago. So I was like, okay, that's very timely, so I will include it. So the hypothesis we had back then was how we can decrease the memory footprint of Java object. So every Java object, it has the body, the fields, the stored fields, and the references that it's in an object. But in the beginning, it has some metadata, like a pointer to its class for very fast reflection, and another word that is mostly for the hash code, the lock bits, and the MISC stuff, and the data. So the idea we had it was that, is it possible to have a mechanism to reduce this overhead, this, let's say, 2 words per object? And one solution that we thought was to actually try to remove the class pointer. So the first word of its Java object, it's actually a pointer to its class. So we said, okay, let's remove that, right? So let's remove this pointer and then store all those pointers into an array in memory. And instead of actually using this the pointer to reference directly the class, now we're gonna use some special bits in order to encode the index in this array where the actual pointer is to the class. So then the question was, and how are you gonna encode these bits, right? How are you gonna, where are you gonna find those bits? And in 64-bit architectures, in all of them, not all 64 bits are used in the memory address. In reality, only the 48 bits are being used. So you have a number of bits that are unused because, I guess, because nobody will ever address 2 to the power of 64 bits memory. And some architectures like ARM and I think Spark, and I think also RISC-V, they can use those extra bits from the memory address to encode some metadata. So you can actually change your compiler when you actually put the address there to use the upper 16 bits in order to store anything you want, right? Anything that your compiler or VM can use. So if you remove the class pointer from the inside the object, and then you use these 16 bits to actually store an index to this in-memory array where you actually store the real pointers, then you could have essentially the same functionality without having to store the extra word for the class pointer in the object. And then we started working on this idea. And the experiment we ran was that, okay, let's take maxim, which is the combination of maxim VM and zsim, and then change the compiler of maxim in order to, or the VM actually, in order to remove this pointer from when allocating objects into memory, and also trying to encode those bits for the index inside the address generation of the compiler. But as soon as you do that, then you need also to change the hardware, because now when the address comes into hardware, it has to understand that this is a special address to chop the low 48 bits, chop the 16 upper bits, and use these 16 bits to actually reference this in-memory array. So we need some hardware support for that. So what we did was, if you look here on the left, we have an object pointer, and each object pointer essentially the first word, it is the CIP, which is the class instruction pointer, the actual address to the class. And then you have another word, which is the misc word, and then you have the actual contents foo of the object. So we remove that, the CIP, and now for every class type, we actually store the address of this class into an array in memory. And we know for each type of class, the index in this array. So now when we actually want to allocate a new object, we actually, every address that we create for the object in our Java program, we use the upper 16 bits to remember the index in this array. And then, so we change in the maxim side, we change the compiler and the runtime. And now in the hardware, we have to implement extra hardware in order to be able to take those 16 bits and actually index this in-memory array in order to retrieve the actual class pointer. That means that we had to change the AGU, which is the actual unit that does the address generation. And also we had to change the load and store unit in order to be able to store the addresses correctly and separate the memory address, the visual address of the object with the pointer. So we did all these changes, and we ran the experiments. These are from the paper. These are many experiments, but let's focus only on the geomean, let's say the average, the geometric means of everything. So in the upper, let's say, cluster of numbers, we have the heap space savings. Means that if we remove from those benchmarks, Java benchmarks, one word per object, how much actually space do we save? And we see that if we combine the elimination of the class pointer with the object compression, which are, let's say, complementary approaches, we can reach up to 25 to 28% less heap. But let's focus only on our solution, the elimination of the class pointer. Just by eliminating one word per object, we can save up to 10% in heap space. And initially, we were a bit skeptical because we didn't expect that of a big let's say, decrease. But when we dug deeper into the results, we came to the same conclusion that I think Steve Blackburn came like 20 years ago, that the majority of the Java objects are small. So you have small objects and in body, like how much data they store inside. And in this small object also, you have these two extra words for keeping data, or even if it's an array, it's even more than 2 words. And by just taking out the class pointer, you can get a lot of savings, especially in constrained memory environments where you don't have a lot of memory. And because you actually save less into memory, because you store less into memory, your traffic to memory, it's much less. So it also correlates to how much energy you spend in the DRAM. So if we go again to the geomean of the bottom figure, we see that it's almost one-to-one correlation. For 1% of less space that you store in your Java heap, you have 1% less energy you have to spend on the DRAM, because this is like a ripple effect. The smaller the footprint, the less pressure you have on the cache, the less spills you're gonna have in memory. There are much more numbers in the paper, also regarding performance improvement, because as soon as you do that, you let's say you use less memory, so the garbage collector kicks less time, so you save times from there. So in general, it is, in our opinion, a solution that justifies the means, because the downside of this approach is that as soon as you put in your critical path in the hardware, extra hardware, you have to get the timings right. So you have to get exactly the same time or very close for decoding the address. And also you have to make sure that this hardware that you put, the extra hardware units you put, it doesn't add too much power in your chip. But if you save 10% in DRAM energy, I think that you're gonna compensate for this extra energy you're gonna spend on this hardware. So the second use case, and the last one regarding technicals, it is a paper that is coming on VE next month. It's about a new, let's say, way of running things, of running multiple tasks on multiple devices. So the hypothesis here is that if I have a system like Tornado VM, that it can split the code into different devices, if I have the functionality to run concurrently different tasks on different devices, assuming I have 2 GPUs to utilize full throttle both GPUs, if I can get higher performance. So what we did to test this hypothesis, we implemented parallel interpreters running in Tornado VM. So now Tornado VM inside, it has an execution engine per device. So if we have 5 GPUs, I'm going to dedicate one parallel interpreter in parallel for every GPU. And then we're going to do some machine learning model to predict which code will run faster on which device, because you don't want to starve your GPUs, and you want to have a very load balancing across your devices. And essentially, if you remember the API that Juan was talking about, in Tornado, you can actually compose different tasks into a task schedule. So you can say, I have a pipeline that consists of 3 tasks. Here it is a blur filter for red, green, blue. And each task, it's actually a Java method. So it's like a function pointer to a Java method. So before this solution, before we introduce MTMD, all those tasks would run one after the other on the same device. So all of them could run on the same GPU. And if I want to use another GPU, I have to take all of them and run it again on the other GPU. But now what we do, we extend Tornado VM to have multi-context bytecodes. So to actually separate the internal bytecodes of Tornado VM and to be able to interpret them in parallel across parallel execution engine instances. So now every hardware device on the system, it gets its own separated and isolated, let's say, interpreter or execution engine instance. And then I can decompose completely my task schedule and send for execution those tasks independently. So if I do that, so what do I gain? So these are, again, these numbers are going to be on the preprint next week. Just to help you understand the numbers, our focus here are the blue colors. So the baseline, which is 1, it is the best numbers that Tornado VM can give us now without MTMD. Meaning that if I run the same code, all the pipeline on each device, which is the fastest, which is of course is done statically offline. So I have to run all of them, see which one is the faster, and then remember it for the next time I run it. So we see that there are a couple of other ways to run on GPUs in literature, but all of them mostly they don't even compete with statically seeing which one is the fastest, and then take this knowledge and implement it in your virtual machine to reuse for the specific workload. But if we use the machine learning model and the MTMD at the same time, we can see that we can get up to 83% faster performance than the best static that Tornado can do. So this is not let's say the best. So our machine learning model is not perfect, of course, but it is of an accuracy of between 85 and 90%. So we can actually predict based on code features, data sizes, and hardware configuration, meaning the raw power of a GPU, which one is going to run faster, and schedule the execution based on this one. But it's also only performance. So if you want to design for energy efficiency, this is future work. So I went very fast through the whole Beehive stack, all the layers, at least introduction, and some examples of how we use this stack in our group to do research. And I would like to, this is the last part of the presentation, I would like to discuss a little bit and get your feedback. So we have been doing this work for many years, like I think now it is 6-7 years of building and building and building infrastructure. And sometimes when we get tired, normally, or when we have to debug multi-threaded bugs, so this is where these thoughts come into existence, we start asking ourselves, does it worth it? So we put all this energy, and sometimes we reflect if we get back the investment that we put in building and maintaining this infrastructure. So some numbers, just to give an idea of the complexity of the whole stack. Currently, we have 52 repositories. Some of them are open source, some of them are closed source, some of them they're going to become open source later, and some of them they will never become open source. It depends the contracts. And we have currently 22 active contributors. And if we take not all the projects, just the flagship projects, we have over 700,000 lines of code, mostly Java, C, C++, Python, and assembly. We have 7 major downstream projects that we have to update regularly and make sure that our tools they are running with the latest version of those tools. Namely, we have OpenJDK, GraalVM, JVMCI, Gen 5, Apache Flink, OpenCL, and OneAPI. We have resolved over 600 public requests, public and private. And we have a very, let's say, the first word that came to my mind was convoluted, but I would say complex infrastructure for integration that consists of GitHub Actions, Travis, and we have 3 in-house servers for regressions for different vendors, devices, hardware that we run our performance testing and our regression testing when we push or open a pull request. So I'm circling back to the first initial, let's say, motivation. So we have been motivating the whole infrastructure by the fact that we need an infrastructure in order to design for performance, security, energy efficiency. So after 6 years, we build this infrastructure, and now we end up to another trade-off, another space where we have to again think how to design. Because now this time, we have this complex infrastructure, and we have to think and balance between 5 new dimensions, mainly the research. So how to use this infrastructure in order to produce 4-star rest papers, how to design our grants around this infrastructure, because essentially we use research grants, meaning that the grants, they have to be aligned with infrastructure so we can reuse it, so we can actually make up for our investment. We have to balance the engineering effort, so when it's good enough in order for us to do research, so when we have to take a breather from engineering, when there are some milestones we have to hit and then pause in order to do our research or write our grants, how much time we should dedicate for providing support for the community. So people are using them and we put them out because we want people to use them, but we are a small team and we need to keep a balance between solving other people's bugs and us doing our research. And of course, we also have to have a vision towards commercialization. Like if a particular sub-project or if a particular component can actually solve a real problem, like that people have in industrial environments, why not commercialize it and generate more impact from the work? So these questions, they have been in our group for, I would say, constantly, and I think they're natural. And some conclusions. So I was discussing with the colleagues, okay, let's gather opinions. So we have this problem here, right? So what is your take? So what would you say is the most important thing for us, for the group, for designing the system? So we came up, actually we didn't came up, we reflected, and then through this reflection, we came up with some realizations of what, let's say, unconsciously doing or have been doing through this year. So the first one was the investment in state-of-the-art systems and to try to keep up with them, meaning that we built an infrastructure, we have to make a selection of tools to build upon, and it's very important, at least if we have the chance or the opportunity to take state-of-the-art and learn it fast or relatively fast, and extend it and use it and be able to downstream and keep up with the latest, the greatest, that's a good choice for us. We have to align our grants with the vision, meaning that we have to find partners that they share the same vision or they have the same problems that our vision can solve for them, and join this consortia in order to reuse our systems in these grants. Normally we avoid to diversify very much, because if we spread too thin, then we lose our domain expertise, and then it's harder for us to let's say do more aggressive and more, let's say, blue sky research, because then we are trying to learn too many things at the same time. Sometimes complexity can become unmanageable, meaning that how do you onboard students, how you solve bugs, how much time you have to dedicate in this kind of activities, solving current cases, you have to have a 100% pass rate or 90% is good enough, you know, these kind of questions. Sometimes you have to make some tough decisions, like to drop some projects that they're not rolling as we expected, or sometimes you have to change our infrastructure because something better came and we cannot compete anymore, or we have hit a dead end with a particular sub-project. And sometimes we do opportunistic development. Like if we see that there is a hot topic in a particular area, then we focus or we shift resources more there. So always have a plan towards commercialization, although it's not the #1 priority, because we are a research group. We always try to let's say, keep up a good level of development and practices that if something becomes a real thing, then the TRL it's high enough in order to transition to a product fast. And the most important that we all agreed was the fact that we have to build in-house expertise. We work with grants, meaning that we work mainly with students and postdocs. And in order to build and maintain this complex infrastructure and have, let's say, a smooth transition between staff and academics and students, we have to have a core development team with a clear vision for growth and development, so that we want people that they are in the team, including not only research staff, even academics, to grow or to have a plan for growth within the research, let's say, group of us, even if we know that most postgraduate associates normally, or it's reality, they regard these positions are a small step towards industry or academia as academics. So nevertheless, we try to make sure that all the staff that it's so much hard work, and the least we want it is to throw this work or to make people feel that this work is for no, let's say, in vain or for no return of investment. Of course, this work has been funded many years by EPCRC in the UK, EU, Royal Society Academy, the University of Manchester, and industry. Here are some references. There are much more. Unfortunately, we are not very good in organizing our papers. So if you need more details about a specific subcomponent or subsystem, please feel free to email me. And yeah, that was it. Presentation, and I'm very curious to hear your thoughts, especially regarding how to maintain this open source LAS project, because I know, for example, Stefan has a lot of work in this aspect.
Yeah, thank you very much.
Thank you.
Well, unfortunately, Stefan seems to have
I do have 1.5 minutes, I think. I think my strategy is to try to not take on too many new projects and try to let some old projects fizzle out at some point. So, but yeah, I know the feeling, and there's always more we would want to do, and there's, yeah, it's hard. I don't know how to do it.
Yeah, I know it's sometimes you get emotionally attached to a project, and you know, you have put so much work there, and although you're, you know, like you know that it's time to say goodbye, but you don't want to, but at the same time you say, okay, but who's gonna do it? So who's gonna continue the legacy? And it's you're always torn in between. And I think for my personal, let's say, well-being, emotional well-being, my objective is to minimize those goodbyes. So to try to keep projects as long as I can running in the group.
Yeah,
I suppose Richard has some
Yeah.
unique insights into that.
Well, I'm not sure if my insights are unique. I mean, I think it's always difficult keeping a group going, particularly in academia when resources are often quite small and there is quite a quick turnover. But you're absolutely right that keeping some core expertise is really useful. What I was going to ask you, I think it's a really interesting talk. I was going to ask you, had you any further thoughts where the work you've been doing could be applied to memory management, garbage collection, etc.?
Hello,
Yeah.
sir. How are you feeling?
Oh, sorry, I have to stop for a moment. Someone has just come in, but hopefully this is being recorded, so you'll be able to. I'll hear your answer. Sorry, middle of a research seminar.
So you have you had the pacing check? It is recorded.
Okay, so I can answer the question. We part of this part of the stack of the Maxine VM was the backport of MMTK. So what we did, okay, we had a bit of a blind spot. So when we started integration of MMTK from Jax RVM to Maxine VM, we didn't know that Steve was creating the second version of MMTK written in Rust. So we didn't know about that. So we put resources to try to create a port of MMTK, which will bring a large collection of memory managers into our stack. And we have it. So the first version is working. The problem now is license. So the license of MMTK is not compatible with the license of Maxine VM because Maxine VM is GPL2. MMTK, it is I think it's dual license between Eclipse and something else. Anyway, they're not compatible. So now we are trying to get all the contributors of MMTK to relicense MMTK to be compatible with the Maxine VM in order to open source it. So when we're talking with Steve Blackburn to help us track down everybody, because we tracked down some of them, but some of them are his students, so we don't know where they are. Then we will have been working on that, and then in MPLR in November, Steve announced the MMTK2 written in Rust, which I think is going to become the priority, or at least the new main core development of MMTK. So going back to the question, so what do we do now? Do we keep pushing to get the Java version of MMTK, which we know is going to be deprecated on infrastructure and continue our work, or throw everything and report the new Rust-based MMTK2? And that's a question we haven't yet answered yet because we don't have a grant for that. So there's no point of answering now unless we get a grant for that. So we postpone this answer for later.
Yeah, Dominic.
Hi, Christos.
Hello.
I was perhaps wondering about the architectural side and how easy is it to I didn't quite understand the mechanism for kind of experimenting with new architectures in terms of maybe simulations or using QEMU or something to sort of, you want to experiment with some new architecture basically. How difficult or easy is it to do that kind of thing here? How does it work?
Yeah, okay, so I think the most difficult part, in my opinion, it is the simulator, because unfortunately the high-end simulators, which means the fast and the accurate ones, are not public. They are being used internally by Intel and ARM, and we don't have access. So we end up using, let's say, less of good quality simulators. Now, if you go to Gem 5, for example, Gem 5, you can actually, it's a QEMU-based simulator. We can run inside the whole OS stack in a software simulator. To run the whole Da Capo on OpenJDK on Gem 5, you need at around, I would say, 6 days, just one run. Okay, which is it's not realistic for us, because imagine for every little change you do in the simulator to add a hardware feature, you have to run a regression of 6 days. So, but Gem 5 is a full system simulator. If you work with a trace-based simulator, meaning that you can actually create the traces of your benchmark and then feed them the simulator, you can get a higher performance. And that's why we went with a ZSIM. A ZSIM, it is somewhere in the middle. It is not a full system simulator. It's not as fast as a trace-based simulator, but it has a very good thing. You can create, you can change it easy. It's not very complicated to change, and it is fairly fast, but it's very accurate. So the paper, I think, when the paper was published about the simulator, it was claiming a 3% an average deviation from the Nehalem architecture, and I couldn't believe it. I said, "There's no way they're so accurate." So we downloaded it and we did the same experiments, and it was indeed 3%. So if you play with, let's say, ZSim, which is really an amazing simulator, I would say it's not very hard to do research. The problem is debugging. You know, like you change the compiler and the runtime at the same time you change the hardware. Normally, if you do co-design, so you hit a bug and then you don't know where this bug comes from. It comes from the compiler, comes from the simulator. QEMU is very slow, in my opinion. It is painfully slow. But yeah, unfortunately, we don't have better tools. Now there is, through the RISC-V, there is a paradigm shift. So RISC-V, because I didn't have a software simulator, I think the Gen 5 port of RISC-V came 2 months ago. They created FPGA-based simulators, the FireSim, on Amazon cloud. So they actually rented FPGAs. They put the design on the FPGAs. Then you could just pay money to run fast on the FPGAs, fast and accurately. And I think this paradigm shift, it's gonna go to other architectures also, like ARM, like FPGA-based simulation.
Okay, thanks.
Welcome.
Are there any other questions?
I had another kind of high-level question, perhaps. Around these parts, we've been sort of talking about the Cherry work recently, the capability hardware stuff that's kind of ARM and Cambridge are working on. So I wondered if you thought about sort of using Beehive in that setting. If you're thinking about, you know, grants and, you know, things to do with it, this is quite a hot area now.
We actually got a grant, to be honest.
Oh, right, there you go. Sorted.
So now we're porting OpenJDK on the Morello platform, which is the Cherry capability platform. So now we're doing that. But the problem there is that, you know, like a compatibility between OS, the infrastructure of Morello, because I think the test beds are coming out, so they're not out yet. So now we're assembling. Now we're adding assembly in the dark. Just we're adding the assembly, waiting for the systems to start testing.
Right, but you can run it on top of QEMU or something, right?
Yeah. That's the problem.
Slow.
You have to for every change that you do in OpenJDK, like every instruction, you have to build the whole JVM, which takes like a half an hour only to do that, and then run the QEMU, and then poof, it breaks. It is the process. It is the problematic one. Right? You don't have these fast turnaround times. For every little change, you have to do like an hour of prep work.
Okay.
Richard, are you back?
Yeah, I'm sorry. I was just going to apologize for my rudeness in dropping out, but I had an interruption that I couldn't avoid. So I mean, I hope there was an interesting answer to my question. I'll look on the recording to see what it was.
I can say that again. No problem, Richard. It was a long answer. Great. Yeah. So I think that when we started doing the Beehive stack, we started porting MMTK to Maxine VM, and we have a port already ready. At the same time, Steve was working on the Rust-based MMTK2, which we didn't know about. Yep. So when we finished our port with the Java-based MMTK, we called Steve to help us track down all the contributors of MMTK, because we had to convince them to relicense it, because the license of Maxine VM and MMTK, they weren't compatible. So we have it, but we can't open source it. And then Steve helped us to find some of them, but then he announced in November the MMTK2 Rust-based. So now our question internally in our group is, what do we do? Do we push towards this, or we scrap everything and we start again with the Rust-based?
Yeah, a difficult problem for you, because they're quite different.
Yeah, Yeah, I know. But as soon as you decide, let's say the old one, then nobody will maintain that anymore, right? So then you're